So far, we have been using transformers as our architecture, and we were agreeing upon using attention mechanism. And we were sort of agreeing with the title of that paper that attention is all you need. But these days, we are actually questioning that claim. Is attention really what we need? Can we use other architectures, perhaps simpler architectures, to do the same thing, to achieve the same results? Don't worry about this architecture yet and the pseudocode. Don't worry about this plot yet. I'm gonna break it apart. First of all, like transformers, we are gonna have L layers of blocks, L layers of identical blocks. They have identical size and structure. They could have different parameters. And we are stacking them on top of each other. We also have tokenized representations for our text. So our text is going to end up being a matrix. It's going to have a length and it's going to have a dimension. So far, so good. We are going to normalize it. We are going to project it. We are going to activate. Then there is going to be some spatial gating unit, which I owe you. I need to tell you what that is. Another channel projection, and then you add the residual connection. So let's not worry about these shortcuts because they're straightforward. They're just additions. Let's not worry about this normalization. This is just a layer norm. We also have that when we have transformers. And in the math that follows, let's ignore the biases. Let's just look at the weights. First of all, we know that X is n by d dimensional. We need to mix across the channels. D is the channel, n is the sequence. We need to mix across the channels. And if you want to do that, you can just multiply from right by a matrix. Multiply X from right by a matrix, push it through a nonlinearity, in this case, Gaussian error linear unit, and that's going to give you Z. So whatever that you have here is after these two operations, channel projection and activation. So this was simple, nothing special. Then you need to mix across your sequence. You need to mix information the same way that your query was paying attention to every other key at your input. You need to somehow find a way to replace that mechanism. You need to mix information across the n dimension, across the sequence dimension. And that one I'm going to explain shortly. But let's say you manage to do that. Now you're after this block or this sub block. What are you going to do then afterwards? You're going to multiply by another matrix from right, and that's going to give you the outputs. And then you can add your shortcuts. And this is exactly what you have in the source code. You have a shortcut, so you're just going to memorize X for a while. Then you're going to normalize X, which is this orange box here. Then you're going to do your projection, which is this operation here. You multiply from right by U. Then you do your activation. And this is this spatial gating unit, which is going to mix information across the sequence. Then you do your projection again, and then you add the shortcut. So that's the big picture. The question is, how do you mix information across your sequence? And that's the spatial gating unit, and it's going to do cross-token interaction. And all you're doing is you take Z, which is outputted after this activation, you multiply it from left by a matrix, which is a learnable matrix. And that's going to have the size of your sequence. And this is what is replacing your attention mechanism. A simple matrix vector multiplication from left. So all you're doing is multiply from right, multiply from left by weights. But then there is a minor catch. You first divide your Z in channel-wise, so you're just dividing it into two matrices that have 1/2 the dimension of the original matrix. One of them, you're going to do this mixing across the tokens or token mixing operation on Z2 and then multiply by Z1 pointwise. And this is this S operation. And all you're doing is MLPs, multi-layer perceptrons. Before I show you that table, in terms of the code, you take X, channel-wise, you split it. This is going to actually give you Z1 and Z2, or you can call them U and V in your code. You normalize V. This is this normalization here. Then you get the dimension of V because you need to know what W you need to multiply that by. And then you multiply by a W. and this is this projection layer, which is multiplying by W from left. And then you multiply them together pointwise. So a pretty simple architecture. How does it perform? And how does it compare to BERT? For training, you're going to use the same setup, the same way that you were training BERT, you're going to be training your architecture, this spatial gating unit architecture, or gMLP, or MLP with gating. If you have BERT base, we know that we have two versions of BERT. One of them is smaller than the other. So there is BERT base, there is BERT large. You can look at the perplexity of your language model to compare BERT versus MLP with gating. And given different architectures, you're getting similar performance. gMLP is slightly worse, but on your downstream tasks, it's doing better on some of them. The other one, when you compare to BERT large, it is actually doing better. And the reason for it is transformers have some inductive bias in them. MLPs have very little inductive bias in them. So they're going to benefit from larger architectures more. So they're more flexible to learn from more data. And that's why, given the same size, this one is doing better when you enlarge your model. But we are not done. You can actually complement gMLP with a small attention head. Rather than having 12 attention heads, each one of them being 64, which is going to give you 768 as the dimension of your hidden units, you can only use one of them. So you can use one head. And that one is going to improve your performance by a large margin on all of these tasks. So a little bit of attention is going to help the model a lot. And how do you actually implement that tiny attention? You still have the same framework that you have X. You're going to do your projection to the attention dimension. That's going to give you your query key value. And then you're going to create your attention matrix, push it through a softmax, and then multiply that attention by the values. So query key value. And this is in addition to whatever that you had before with your gMLP. So this is exactly this unit. You are changing it slightly, and you're just adding the outcome. How does it perform? Transformer and gMLP, as you increase their size, gMLP is going to do better. It's going to cross transformers at some point. A little bit of attention is going to help gMLP a lot when it comes to perplexity of your language model. In terms of your downstream tasks, it depends. If you're doing SST or natural language inference, you're going to get different results. Let's compare gMLP to transformer. gMLP is doing better than your transformer. And the other one, if you add attention, it's going to help a lot. There's small, tiny attention. But the story is reversed when it comes to natural language inference. gMLP is doing worse than transformer. So transformers are worse than gMLP for this task. gMLP is better than transformers here, and it is worse than transformers for the other task. But a little bit of attention helps gMLP. Any questions about this slide? And this was Stanford Supplementary back data, where you have only positive and negative reviews. So this is a sentiment analysis task, and this is a natural language inference task, where you have pairs of sentences. Any questions about gMLP or AMLP? Was everything clear? Okay, perfect. So the message is attention is probably not all you need. But one thing is for certain is these projection layers and that inverted bottleneck type of a layer when you go from low dimension to high dimension and then back to low dimension is really crucial. But the way that you pay attention and model attention could be different. And one cool thing about gMLP is that its cost is actually linear in your sequence length. You just have a matrix and you multiply it by another vector. So the computational complexity is order n to compute this multiplication.